So,
Introduce.
yes, you may start. Today's speaker is Mykola Khrypchenko from University of Porto. The title of the presentation, Transposed Poisson Structures. Please.
Thank you very much. So this talk was quite unexpected. I had little time to prepare it, so I apologize for eventual mistakes on the slides. Well, the talk is based on 5 papers joined with Ivan. 3 of them were published this year and 2 of them are submitted. All of them are about description of transposed Poisson structures on some class of Lie algebras. So I start with some general facts, some classes of transposed Poisson structures that you can define on arbitrary Lie algebra. And then I move on to some concrete classes of Lie algebras and description of TP structures on such classes of Lie algebras. Transposed Poisson algebra is an algebra with 2 multiplications. It is commutative associative algebra with respect to the dot, and it is a Lie algebra with respect to the bracket. And the so-called transposed Leibniz law holds that relates these 2 structures. So when you multiply z by the bracket of xy, you have this sum of brackets in which you apply z on the left or on the right, doesn't matter, to one of the factors of this bracketed product. And taken into account that there is this coefficient 2 on the left-hand side. So given a Lie algebra, I call a transposed Poisson algebra structure on this Lie algebra a commutative associative multiplication on the same vector space, which makes this triple a transposed Poisson algebra. So if you have a fixed Lie algebra, you can ask what are the transposed Poisson structures on this Lie algebra. How can you describe all the commutative associative multiplications on this vector space, which jointly with this bracket makes you a transposed Poisson algebra. And I will abbreviate transposed Poisson just to TP structure, or TPA structure, transposed Poisson algebra structure, if you wish to distinguish from transposed Poisson superalgebra structure. But in this talk, I will only speak on transposed Poisson algebra structure, so TP structure. Well, related concept and very important in the description of transposed Poisson structures is the concept of a half derivation. Given an algebra, not necessarily a Lie algebra, in fact, over a field of characteristic different from 2, a linear map is a half derivation if it satisfies a Leibniz law with this coefficient 1/2 on the right-hand side. That's why I ask that I require that the field has characteristic different from 2. These maps, they form a vector space, and the vector space of all half derivations will be denoted by delta of L. Well, just the vector space, the bracket of half derivations, of 2 half derivations, is not necessarily half derivation, so we'll be just talking on vector space of such maps. So, if you have an algebra with 2 multiplications over a field characteristic different from 2, let us denote by LZ the left multiplication with respect to this dot. So if the bracketed operation satisfies the Jacobi identity, then your triple is a transposed Poisson algebra. If you don't leave, this left multiplication is a half derivation of the Lie algebra structure for all Z. And that's why the notion of half derivation is very important in the description of all the transposed Poisson structures. So let us consider some classes of half derivations and the corresponding classes of transposed Poisson structures. First of all, a trivial half derivation is just the multiplication by some fixed scalar from your field. for any scalar, this is a half derivation. It's called trivial. It corresponds to the so-called trivial TP structures. These are those structures that are just zero multiplications. Why is this so? Because there is this, well, important corollary, which is, in fact, you can call it lemma, that if the dimension of your algebra is greater than 1, then, and all the half derivations are trivial, then all the TP structures are trivial. This holds for any Lie algebra of dimension greater than 1. In the dimension 1, your Lie algebra is abelian, and so this is not true, but in this case, the Lie product is 0. So any commutative product, a commutative associative product will be a TP structure, but it's not interesting. Okay, another class of half derivations is, I will call them central valued half derivations. So let us denote by Z of L the center of the Lie algebra, and I use the usual notation for the square of the Lie algebra. Any linear map with values in the center that annihilates the square is a half derivation. In fact, it is a delta derivation for any delta. In particular, it's a half derivation. I call them central valued. They correspond to the following transposed Poisson structures. Well, let's consider first a more general fact that was proved in the article by this group of Chinese mathematicians. If we have a Lie algebra and a commutative associative product on the same vector space, then this triple is at the same time a usual Poisson algebra and a transposed Poisson algebra, if and only if both products annihilate each other. So in some sense, trivial situation. If all the mixed monomials of degree 3 are 0. So such transposed Poisson structures will be called to the TP structures of Poisson type. So they are at the same time usual Poisson structures. And I would like to give some constructive way to define these structures, and in practice, in some cases that appear in the practice. For example, if you have a Lie algebra, yes, consider you have a square, consider a complement of this square in your algebra. Of course, if the square coincides with the algebra, then the complement is just 0. But in general, it's not the case, and you have a complement, just a vector space complement. Of course, it's not unique, but just fix one. And consider a commutative product defined on this complement with values in the center. Again, center can be 0, so this can be just a trivial product, but in general, it's not the case. And this product extends to the whole algebra just this way. You have these pairs, you have these sums. Okay, any element is unique, it's uniquely represented as the sum, the element of V and the element of the center, and you just multiply the first coordinates, those elements that belong to the complement, since you know how to multiply them. So multiply them. And okay, so this is a commutative operation on the whole algebra, and it satisfies the transposed Leibniz law with respect to this bracket. However, it's not necessarily associative, but in some cases you can control this associativity. For example, if the center has trivial intersection with the square, then you can choose this V to be a subspace that contains the center, and in this case, the extended operation is associative if and only if the original operation was associative. Another situation that appears in the practice as well is when the center is inside the square. In this case, all the monomials of degree 3 will be automatically 0, so you it's not it's not important whether the operation start with associative or not. So any operation will extend to an associative operation on the whole algebra in this case. So you just take any commutative operation and it extends to a transposed Poisson structure, and vice versa. Any transposed Poisson structure restricts to a commutative operation on this component. So you have some kind of description of transposed Poisson structures of Poisson type in this case. So yes, it's written here that such the operations dot is a TP structure of Poisson type. Now, these are two cases that happen in those 5 papers that I have mentioned above. So for me, it's enough to consider only these 2 cases, but of course not all the cases that appear a priori. Well, another class of half derivations and the corresponding class of TP structures. Okay, this was quite new. It was discovered recently in our last paper that appeared today on arXiv. So if you have an on the center of the square of the Lie algebra, then you can consider the associated inner derivation. So C is fixed, and it takes on A just the bracket with C. So since C belongs to the center of the square, this map acts on the squares, on the square brackets trivially, so it gives 0. And since we know that it's an inner derivation, then the other side of the Leibniz identity will also be 0. So multiplied by delta, arbitrary delta will be 0. So this will give you, in fact, delta derivation for any delta. In particular, it's a half derivation that I will be called inner half derivation. Again, it's not necessarily non-trivial because, of course, you can have center of the square equal to 0. So you can have an Lie algebra which has square equal to itself and the center trivial. So it will give you trivial half derivation. But in general, not the case. And as we will see, in some cases, it's not trivial. Okay, the corresponding TP structure is the following one. You fixed C as above, the element of the center of the square, and define the multiplication on your vector space by taking these triple brackets. In fact, this particular monomial is associative, so it doesn't matter how we put the brackets here. And moreover, this new product is commutative, and it satisfies the transposed Leibniz law. So it is a transposed Poisson structure on your Lie algebra. And okay, so in literature, this new operation associated with a given operation, when you insert a fixed element between the other 2 given elements, it has several names. It's called mutation in the case of associative algebras, at least. So I called it mutation here. So this is a mutation of the original Lie bracket. Later, we will see that some TP structures, they are also obtained as mutations of some other associative product on the same vector space. So just not to confuse this TP structure with those TP structures that we will see later. So I will call such structures mutational structures. So this is defined in terms of the original Lie bracket on your Lie algebra and fixed element of the square, of the center of the square. Now, when you know several TP structures, you can sum them, so you can consider their sum. More generally, the sum of 2 binary operations is the new operation whose result is just the sum of the two operations here, as written here. Of course, the sum of two associative operations need not be associative, but it is associative if the two operations annihilate each other. In this situation, I call them orthogonal. Orthogonal means that all the mixed monomials of degree 3 are 0. So the square of one operation is inside the annihilator of another one, and vice versa. In this case, the sum of two orthogonal operations will be called the orthogonal sum of these two operations. So the orthogonal sum of two TP structures is a TP structure. And if you have a mutational TP structure and a structure of Poisson type, their sum is always orthogonal, so they are always orthogonal to each other. So their sum is always a TP structure. Again, it may happen that all of them are trivial, so their sum will be trivial. But if you have non-trivial Poisson structures, if you have non-trivial mutational structures, their sum may be another non-trivial TP structure on your Lie algebra. So these are structures that can be defined on any Lie algebra in terms just of the original Lie bracket. Okay, well, it's some fixed element or some fixed product on some subspaces. Okay. Now let us pass to the second part of the paper, the main part of the paper, where I can give the description of TP structures on some classes of Lie algebras. So these are Lie algebras that I'm going to consider. Well, I'll start with block Lie algebras and then pass to weak type algebras, then general block Lie algebras. Observe that general block, some of these algebras generalize other classes of Lie algebras in this list. For example, general block Lie algebras generalize block Lie algebras BQ. BQ is a particular case, but chronologically, we classified first this class of Lie algebras. In fact, in this general case, we used another method, another approach. So, I mean, no, well, the method was the same, but the calculations were different. So, well, again, these generalized with algebras, they are a generalization of weak type algebras. It's some subclass of weak type Lie algebras. But I cannot just consider one of this more general class because I used this more particular result in their description. So, and again, chronologically, this is the right order. Again, incidence Lie algebra, they generalized upper triangular matrix Lie algebra, but we used in the description of TP structures on incidence Lie algebra, we used the result about upper triangular matrix Lie algebra, so we can just skip it. Okay, so let us start with block Lie algebras. So this is a class of Lie algebras about a parametric family of Lie algebras parameterized by complex numbers. It has basis, it's infinite dimensional Lie algebra, whose basis is indexed by ordered pairs of integer numbers. And the multiplication table is as follows. Well, in many of these algebras, in block Lie algebras, in weak type Lie algebras, in in general block Lie algebras, the product is some modification of the group algebra product. So all of these algebras that I mentioned, all the three classes of Lie algebras, they have basis indexed by some group, a Boolean group. And they have product which reminds the group algebra product, but it has some coefficient which makes it, in fact, a Lie product, not an associative product. In this case, we have the following coefficient, which depends on the indices and depends on the parameter Q as well. And it originally, at least for me, it was the original paper that this class of algebras appeared. This was the paper of this group of Chinese mathematicians. However, they have some restrictions on the parameter and on the indices of these basis elements. But in fact, we considered the general case and studied this case. As I said, this class of Lie algebras B of Q is a particular case of more general block Lie algebras. These were defined in the paper by Richard Bloch in 58. Okay, so we have an abelian group, a field, and we have two maps. One of them on A is additive, another one of two parameters, and it's the additive and antisymmetric. And we define, we consider an algebra whose basis elements are indexed by the group elements, and define this product, which involves functions f and g. Well, this product is always antisymmetric, as you may see, but it need not satisfy a Jacobi identity. So when does it satisfy Jacobi identity? First, if and only if, in fact, G is zero map, trivial map. If not, F is some kind of bracket of G and some other map H, some other additive map H. Let's see why the class of algebras BQ is a particular case. Well, in this case, A is just the direct product of Z times Z, and you take G, the following map, and you take F, the following map, B additive map. If Q is non-zero, if Q is zero, then G is zero, and it's always a Lie algebra. If Q is non-zero, then you can express F in terms of G and H, where H is the following map. So I divided by Q. Okay, let's see what are TP structures on these algebras. First of all, on B of Q. If Q is non-integer, then all of them are trivial. If Q is integer, then we have only one up to isomorphism, non-trivial TP structure, and it's given us by the following multiplication table. In all of these multiplication tables, I just give non-zero products. Well, possibly non-zero. In fact, this is non-zero. Yes, but in general, I give just possibly non-zero products. Those products which are not presented in the table, they are zero. So what can we say about this product? If Q is zero, you can see that this is just L0 square equal to L0. So it's just a unique up to isomorphism non-trivial product defined on one-dimensional algebra, subalgebra, and extended by zero. So this is just Poisson type TP structure. If Q is non-zero, then you see that all the you have the square of two. You have the square of one basis element equal to another basis element, and all the rest of the products are zero. So when you take all the monomials of degree 3, you have zero. So all the monomials of degree 3 are zero, and we have that another situation that I mentioned when you have the center inside the square. Okay, so all of these structures are of Poisson type on this Lie algebra. In fact, this holds in a more general situation for general block Lie algebras. But again, the proofs are different and we need some assumptions on the maps. We assume that F is non-degenerate. This means the following, that if FAB equals 0 for all B, for some fixed A and for all B, then this A should be 0. Moreover, we consider only fields of characteristic 0, and in this case it implies that A is torsion-free, so it can be a finite group. And in this case, we can also describe the center and the square of this algebra, and just to see that how they appear, this description appear in the final theorem. So if G is a trivial map, then the center is spanned by one basis element, U0, and the square is spanned by all basis elements corresponding to non-zero element of the group. So you see that if G is 0, then the center and the square have trivial intersection, and this is one of the cases that we saw that in that description of structures of Poisson type. And if G is non-zero, then the center is spanned by those basis elements which are solutions of the following system of linear quotients, or linear additive equations on your group. And in this case, the square is spanned by all the solutions of this system of inequalities. And you see that in this case, the center is inside the square, because if h plus 1 is 0, then h plus 2 is non-zero. And yes, the center is inside the square, and we are in that second situation, so we can talk about TP structures of Poisson type. And in fact, we again have the structures of Poisson type. So first of all, the case of G trivial map, we have only one trivial TP structure on this algebra, and is given by this: the square of U0 is U0. We have unique non-trivial product on one-dimensional subalgebra, and we extend it by 0 to the whole algebra. Of course, it gives you a TP structure of Poisson type. If G is non-zero, the description looks more complicated, but in fact, if you remember that description of TP structures of Poisson type in the general case of description, then it's not that surprising, maybe. Okay, we see if there are solutions of the system of quotients G of A equal to 0, H of A equal to -1. If there are no solutions, then all the TP structures are trivial. Otherwise, we consider all the solutions and consider all the basis elements to corresponding to these solutions. And this is, in fact, the center of your algebra, as we have seen. And this subspace is a complement of the square of your algebra. And you see that if your element belongs to the center, then it automatically belongs to the complement. Sorry, it belongs to the square. Well, so you just take all the commutative products defined on this subspace with values in this subspace, and automatically all the monomials of degree 3 will be 0, so you just extend it by 0 to the whole algebra. All the monomials of degree 3 will be 0, and it will satisfy the transposed Poisson law, and this will give you a transposed Poisson structure of Poisson type. Okay, so this fits into that general description of TP structures of Poisson type. Okay, so now let us pass to Lie-type Lie algebras. Let me mention that in one of the papers of Ivan with collaborators, they have described TP structures on their classical Lie algebra, and they were just mutations of the group algebra structure on the on the integer numbers. In fact, in some cases, this generalizes to Lie-type Lie algebras. Okay, let's see. Again, this is a Lie algebra defined in terms of some abelian group and some map on this abelian group. But we do not require this map to be additive. In fact, it's some map which results in a Lie algebra. Okay, we define the product on the basis. Okay, basis is indexed by the group elements, and the product is defined in terms of the map F this way. We see that it's automatically anti-commutative, but it's not necessarily a Lie algebra. We can observe that we can always assume that F sends 0 to 0 by just slightly modifying this map F. If it's not this of this type, and this new modification does not change the original product. So we can always assume that f is 0. F of 0 is 0, and we can also assume that f takes at least 2 elements, because otherwise this map is abelian. This product is trivial in this, and this Lie algebra is abelian. Okay, so this is the condition that this map should satisfy to give you a Lie algebra. So this vector space is a Lie algebra if and only if the following holds. We can see that for the classical case, to get the classical case, we just take the abelian group to be the integers, of course, and the map F to be the identity map on the integers. Okay, well, if you consider integers as a subgroup of the complex numbers, so this is a map from G to your field F, so field complex numbers. Okay, this F always satisfies the following two conditions. Which is important for us is that those elements which are mapped to 0, they form a subgroup of gamma, not necessarily a normal subgroup, but, well, okay, so sorry, normal because it's additive, it's an abelian group, sorry. So yes. So, but as you can see, this map not necessarily factors through an epimorphism. So, but some kind of. Okay, let's see. As I said, we do not assume that the map is additive in general, but if it takes at least 4 elements, that it's automatically additive. This follows from that condition on F. This one can be proved, and it was proved by Yu in his original paper where he defined these algebras. If F takes exactly 3 elements, 3 values, then it factors through a group epimorphism onto the group of 3 elements. And if F takes 2 elements, then in fact, well, you can just define your F, you can just take an arbitrary subgroup of gamma and define your F by 0 on gamma 0 and by 0 on this subgroup and by some non-zero element otherwise on elements outside this subgroup. So, and if F will satisfy this condition. So in this case, you cannot say, in fact, a lot about this map. Okay, let's consider these 3 cases and what's going on in the 3 cases. If F takes at least 4 elements, then F is additive. And in this case, it's easy to classify the TP structures. In fact, the classification is very similar to that in the paper by Ivan, in the case of the original classical with algebra. So all the TP structures are mutations of this product, which is in fact the group algebra product. So just observe that these are not mutations of the original product, Lie product. These are mutation of some product that you can define on your vector space. That is the group algebra product. So mutational structures that was defined in the introduction, they are defined in terms of the original bracket. These products that are mutations of some other product on the same vector space, they are defined not in the terms of original products. So okay, but anyway, they can be described. In the case where F takes exactly 3 values, you have a slightly more complicated description. And you have, okay, in this case, you know that F factors through a group epimorphism. So you have your gamma 0 is a subgroup of index 3. So you take the cosets, so it induces the decomposition of your vector space as a direct sum of 3 subspaces. In fact, it's a Z3 grading with respect to the group algebra structure on this space. Okay, so I can consider these subspaces with the group algebra structure. But again, as I said, since this is a grading, they are not they will be not closed under the original group algebra structure, but they will be closed under some mutation of this group algebra structure. In fact, if you take B to be the element which belongs to the subspace corresponding to the inverse in this group of order 3, then the mutation will belong to the original subspace. And in fact, all the TP structures will be direct sums of these mutations. So direct sum of 3 structures, each of which is a mutation of the group algebra structure, but mutation by an element which does not belong to the same subspace, which belongs to the complement, not the complement, but the subspace corresponding to the inverse in the group of order 3 corresponds to the opposite number modulo 3. Okay. In the case of F taken exactly 2 elements, 2 values. Again, in this case you will have mutations, but in this case you can also have some mutations with respect to some truncated elements, let's say. If B is an element of this algebra, then let us denote by B0 the part of this element which corresponds to the indices belonging to gamma 0. And let's define the operation as follows. This is just a mutation if both alpha and beta belong to gamma 0, just usual mutation of the group algebra structure. If one of them belongs, another one does not belong, then we define it by a mutation with respect to B0. And if both do not belong, then we define it by 0. And this is the description of all the TP structures in this case. Let us pass to the case of generalized with algebras. Well, the definition is as follows. Now you take again an abelian group, just written additively in this case, but you also have a vector space, a fixed vector space, and you have a map of two variables, one of them from B, another one from A, with values in the field as always. This map should be linear in the first variable and additive in the second one. And in this case, you can consider this tensor product of the group algebra with this vector space over F. And you define the Lie bracket on this tensor product as follows. On the group algebra part, it's usual, it's natural, just the operation in the group. But on the vector space part, it's this linear combination of V and W, where the coefficients depend on this map. You can show that this is always a Lie algebra, and it's called a generalized with algebra. It was defined by Djokovic and Zhao in this paper. Let us see why it's generalized with algebra. Why it's a generalization. We always assume that the map, this map of two variables, is non-degenerate, in the sense that if A is annihilated by all the elements of V, then A is 0. And we'll also assume that the field has characteristic 0. So again, it implies that A is torsion-free. And if the vector space has dimension 1, yes, so we define a map, any map of two variables is uniquely defined by this value on A, right? So we fixed V and A is varying, so we can define a map on A with values in F this way. And if we write the definition of the width type Lie algebra given above, we see that it gives you exactly this algebra. So it's isomorphic. So we see that this generalized width algebra, they in fact generalize width type Lie algebra corresponding to additive injective maps. Not every width type Lie algebra, but some subclass of additive maps. And in additive case, we know that everything is simple, so the description of TP structures is simple. And in fact, when the dimension of the vector space is greater than 1, then it turns out that the TP structures are trivial. And if the dimension is 1, we are in the case considered above. So we have the TP structures that are mutations of the group algebra structure, which in terms of this, the elements of this algebra can be written as follows here. So we have the description of TP structures in this case. Again, either mutations or trivial. Let us pass to the case of, now again, all the Lie algebras that we have considered so far, they were Lie algebras defined like the Lie bracket was defined in terms of some function. Now let us pass to Lie algebras that come from some associative algebras, some well-known associative algebras, and we start with matrix algebras. We consider the full matrix algebra, Mn of f, under the commutative product, and we consider its subalgebra of upper triangular matrix algebras. We denote by delta the identity matrix. This notation comes from the theory of incidence algebra that we will be using, and these notations of matrix units as well. So Eij will denote matrix units. In the case of T and F, you know that I should be less than or equal to J. They span the whole algebra. Yes, and everybody knows that the center of this algebra is one-dimensional, so just formed by scalar matrices. Everybody knows that the square of this algebra is the algebra of traceless matrices. Yes, it has the following basis, for example. In the case of upper triangular matrices, the center is the same, and the square is spanned by Eij, where I is strictly less than J. And we also need the center of the square. It is, in fact, if n is equal to 1, it's trivial. If n is greater than 1, it's one-dimensional, spanned by this basis element, by this matrix unit. Okay, we first described the TP structures on the upper triangle matrices. We have two cases here, n greater than 2 and n equal to 2. If n is greater than 2, we have two classes of TP structures of Poisson type. Okay, we know what it is. And the orthogonal sum of any TP structure of Poisson type with some fixed TP structure. When we wrote this paper on the description of TP structures on matrix algebras, we hadn't yet defined what a mutational structure is. But now I can just use this terminology. I can observe that this is, in fact, a mutational structure, because this is just the triple bracket with the fixed element of the square of the center of the square. What it is, in fact, it's minus E1n, as you can see. Right. If n is equal to 2, then apart from these two families that also appear, we have another family, which is, in fact, a non-orthogonal sum of a TP structure of Poisson type with this family of structures. And what kind of structures is it? It's not that clear, in fact, but we will see in the case of incidence algebra what it is. We will have a description of these structures. Regarding the full matrix algebra, Using its decomposition into the direct sum of its center, one-dimensional subalgebra, and its square, you can easily prove that there's only one up to isomorphism non-trivial TP structure on this algebra, and it's given by this multiplication table. And it is, of course, of Poisson type, because you just multiply the two elements of the complement of the square, and the result belongs to the center. It has even a simpler description. It's just the extension by zero of the product delta square equal to delta, where delta, I recall that delta is the identity matrix. Okay. Of course, it's of Poisson type. Now let us pass to the case of incidence algebras, where maybe the description's more complicated than in the previous cases. I will work only with finite posets. Okay, I always work with fields of characteristic 0, but to define a Lie algebra, I do not need the characteristic, okay? So for the finite poset, the Lie algebra can be defined, it's just the semigroup algebra of the following semigroup. I consider the ordered pairs x, y, and I multiply them as follows. I can just glue them if it's possible, otherwise the product is 0. It's an associative algebra. Its identity element is this EX, where I use the following notation. I denote by EX, small x, the basis element EXX, and E with capital in this, where capital letter denotes a subset of x. I denote just this sum of basis elements. So E with capital X means the sum of EXXX for all x. And this is the identity map, the identity element of your instance algebra. And I will use this notation for any element of the instance algebra. This written in as the sum of its base, the sum written in the basis, right? As the sum of basis elements with some coefficients in the field. Incidence algebra, they generalize the upper triangular matrix algebra, and they also generalize the direct product. In this case, you have the set 1 up to n with usual partial order. And in this case, you have a trivial partial order. And your incidence algebra, if X is a finite subset of cardinality n, so it's always isomorphic to a subalgebra in this algebra, and it always contains the algebra isomorphic to Kn. So it sits between these two algebras. Right, so some subalgebras of this algebra, the diagonal subalgebra, okay, so this is that algebra isomorphic to the direct product of the field copies. This is spanned by Ex. Its center is spanned by these diagonal maps, diagonal elements, which correspond to connected components of X. And we will be considering only X, only connected X, so our center will be the same as in the matrix algebra, spanned by the identity element. Its square as a Lie algebra, so we consider, okay, I haven't said that, we are considering incidence algebras under the commutator product. So its square as a Lie algebra is spanned by EXY, where X is strictly less than Y, and its the center of the square is spanned by EXY, where X is minimal, Y is maximal, and X is strictly less than Y. You can see that I is the direct sum of its square and the diagonal subalgebra. So the diagonal subalgebra is a complement of the square, and we can see that the center is inside this complement. So we are in one of that cases that were considered at the beginning of the talk, where we can describe the Poisson type structures in an easy way, just extending some product on some subspace. Okay. Okay, our setting is finite connected posets and fields of characteristic 0. You have TP structures of Poisson type on this algebra, and they are of the following form. You have product of two diagonal elements, diagonal basis elements, and it's a multiple of the identity element, which depends, whose coefficient depends on xy. This map should be symmetric to give commutative product. And for the associativity, it should satisfy the following functional equation, which I will not be well, just in any particular case you can classify it up to some extent, but I will not be. It's not possible to do it in the general case. So just any commutative associative product of this form. Okay. Regarding the TP structures, well, nutational TP structures, you fix one element of the center of the square, and it gives you the mutational structures of the following form. So again, you have multiplications of basis elements belong to the diagonal subalgebra. Now you have product nu xy exy whenever x is minimal, y is maximal, and x is less than y. If the two elements are minimal and coincide, you have the following sum corresponding to all the maximal elements greater than x. And if both are maximal, you have all the basis, all these elements where u is minimal and less than x. Okay, and you apply also nu to these pairs. So this nu appears in all the products, and the rest of the products are 0. Moreover, you can apply a suitable automorphism to make this coefficient to be 0 or 1. Those non-zero you can make to be equal to 1. Okay. Now, in fact, these are not all the TP structures that appear. We have also some structures which will be called lambda structures, and they are defined as follows. So we have a pair of elements of x. I will call them extreme if they form a maximal chain. This means that x is minimal, y is maximal, and there is no element between them. Moreover, I will require that there is no cycle that contains x and y. If the poset has no cycles at all, then okay, no problem. Any maximal chain of two elements is extreme. Otherwise, I can take care of that. I will denote by this x squared e all the extreme pairs in X. They not necessarily exist, of course. In some posets, they do not exist. Okay, now if I fix an extreme pair and some element u0, I can say that this extreme pair is positive with respect to u0. I write this way, the sign is 1. If there is a path starting at u0 and ending at this given extreme pair. Otherwise, I can show that otherwise there is a path starting at u0 and ending at yx in the opposite direction. So there are only two alternatives. Otherwise, either you have a path starting at u0 ending at xy, or you have a path starting at u0 ending at yx. Only two possibilities. In this case, the first case, the sign is 1. The second case, the sign is -1. Just write this way to use it in the formula. Now, if I have two elements, I can say that they are on the same side with respect to some extreme pair if there is a path from one to another that does not involve neither xy nor yx as edges. Otherwise, where there is a path which involves one of them, I can say that they are on the opposite sides. And again, I can show that if there is one path that does not have, then no path can have one of these edges. And if there is a path having xy or yx, then any other path will have xy or yx, any other path from u to v. This follows from the fact that xy does not belong to a cycle. I will fix u0 and I will denote by vxy all the elements which are on the opposite side with uy with respect to xy. Okay, and this, so given any map defined on extreme pairs with values in the field, I can define the multiplication. So given an extreme pair, I multiply exy and the result equals lambda xy exy. And exy ey is minus this product. And if I have two elements two diagonal basis elements where the pair xy is extreme, then the product will be the following diagonal element, yes, which involves the lambda and which involves the sign, depends on the sign. And if I have two equal minimal elements or two equal maximal elements, so the corresponding product will be the following sum of diagonal elements, which involves the signs and which involves the lambda. And it looks very similar to the description to the mutational product, but it involves diagonal elements on the right hand side, not the elements belong to the center of the square. But the formula is very similar, and it also involves this sign here. Well, it can be shown, but not that trivial, but that any lambda structures this way, for any lambda, it's a TP structure on the instance algebra, and it's orthogonal to any structure of Poisson type. And it can be shown that the sum of any mutational structure and any lambda structure is again a TP structure. They are not orthogonal, but their sum turns out to be a TP structure as well. So the sum of Poisson structure, mutational structure, and lambda structure is a TP structure, and the converse also holds. All the TP structures on the instance algebra of a finite connected pole set over a field of characteristic 0 are of this form. They are sums of structures of Poisson type, mutational structures, and lambda structures. Okay, I have also prepared some examples. I think I have no time for that. So I can see that in the case of this general effect on incidence algebra, it just generalizes the case of upper triangular matrices. So I have Poisson type structure, I have mutational structure whenever n is greater than 2. And in this case, I have no extreme pairs, no lambda structures. So in the case n equal to 2, I have only one pair, which is extreme. So choosing u0 equal to 1, we have this subset v1, 1, 2 equal to just one element, 2. And we have the corresponding, it's positive with respect to u0, and we have the corresponding lambda structure here. One can show that these structures are just isomorphic to that structures described above in the case of upper triangular matrix algebras. There are more interesting cases. For example, if you have a V pole set, a pole set of 3 elements, one minimal element and 2 maximal elements, which are above this minimal element, then you have 2 pairs which are extreme, and of course you have, apart from structure of Poisson type and mutational structure, that are as follows. You have lambda structure, which is as follows. And there is another case, the so-called, well, another interesting example, the so-called 2 crone. This is a 4-element pole set. It has 2 minimal elements, 2 maximal elements, and any minimal element is less than or than any maximal element. So you have 4 relations. And since this pole set is a cycle, it has no extreme pairs. So it has 4 maximal chains. 4 pairs form a maximal chain. So, but they are not extreme because all of them belong to a cycle. So in this case, you have no lambda structures. It's interesting because this subset, this pole set, often appears as a counterexample to some theorems. So the incidence algebra of this pole set, it has some bad behavior with respect to some other questions. But in this case, it has nice behavior because it has no lambda structure. It's only structure of Poisson type and mutational structure, and there's some. Okay, so this is all I prepared for today. You can see the 5 papers that I have mentioned. So we have this paper published, this is published, this is submitted, and this is submitted, this is published. Okay, thank you very much.
Thank you. Any questions?
See if there are questions in the chat.
No, in chat there is no question.
But I don't see, I cannot see the chat, but okay, so if no question. Thank you for the attention.
No questions? If there is no questions, thank you very much.
Thank
And
you.
we can finish today's seminar. Thank you.
Thank you.